Hello everyone, my name is Jaydev Naram and I'll be presenting the paper A Riemannian Approach to Extreme Classification Problems. This work was done by me and Tanmay Kumar Sinha under the guidance of Professor Pawan Kumar at C-Star Lab IIIT Hyderabad. In binary classification or multi-class classification, we try to classify an item into exactly one of the two or L classes. But in the multi-label classification problem, an item can belong to more than one class. In the extreme setup, the number of labels is extremely large, usually in the order of 10 power 5 to 10 power 6. To define the problem formally, we are given feature matrix X and corresponding labels matrix Y as the training data. The features matrix contains n feature vectors, each of which belong to Rd so that it is of the size n by d, and the labels matrix contains L d-dimensional binary labels of these n feature vectors so that it is of size n by L. In the test data, we are given an unseen d-dimensional feature vector x for which we have to predict an L-dimensional binary label y. The previous work can be broadly classified into four categories. First, the one versus all methods, which involve splitting the classification task by training multiple binary classifiers. State-of-the-art one versus all approaches like DiceMech, PPD Sparse, and Bonsai give good prediction accuracy when compared to the other methods, but they are computationally expensive to train and they also have high memory requirements during training. The next category of methods is tree-based methods, which aim to partition the feature and label space recursively to break down the original problem into more feasible small-scale subproblems. Examples include pfast RXML, fastXML, and craftML. These methods generally have fast training and prediction times but suffer in prediction performance. Next, the embedding-based methods, which use low-dimensional embeddings to approximate label space. Recent methods use multiple local embeddings to achieve better performance. Some examples are SLEEC, RXML, and EXML DS4. And finally, the deep learning-based methods, which have recently gained attention. These methods generally rely on deep learning models and have very good performance, but are also computationally very expensive. Examples include Attention XML, X-Transformer, and Light XML. Our proposed method is an embedding-based method, so we start by discussing the global embedding model. We model the relationship between the features and labels by a low-rank matrix given by equation 1. Note that here we are using the entire dataset. Equation 1 has a closed form solution that can be computed using SPD of X and Y matrices. Thus, the problem is not scalable to large datasets. To resolve this issue, SLEEC proposed a local embedding model in which the training data is split into C clusters using k-means clustering, and then a local embedding is learned for each cluster separately. Specifically, for the ith cluster, XI-YI, it solves optimization problems 2 and 3. In equation 2, the labels matrix Yi is approximated by a rank R matrix Zi, which is later used to learn a linear regressor Vi in equation 3. We focus on problem 2 and note that by setting M equal to ZZ transpose, we get an equivalent problem 4. Instead of the inequality constraint, we enforce a fixed rank constraint in the above problem to obtain problem 5. The set S plus NR is the set of all n by n symmetric positive semi-definite matrices of rank R. This set is a Riemannian quotient manifold, and problem 5 is an optimization problem on Riemannian manifold. To solve problem 5, we employ Riemannian conjugate gradient algorithm. It is an extension of the nonlinear conjugate gradient algorithm to the Riemannian setup. Here we show the pseudocodes of nonlinear CG and Riemannian CG. We apply nonlinear CG to the unconstrained version of problem 5 as given in equation 6. For the sake of simplicity, the details of choosing beta and alpha are ignored. The key differences between the two algorithms are colored in red. In the initialization step, RiemannianCG requires a point on the manifold. In line 2, the Euclidean gradient of the objective function is replaced by its Riemannian gradient on the manifold. And due to the non-linearity of Riemannian manifold S plus and R, we invoke vector transpose T to perform the vector addition in line 4. Similarly, to update the point on the manifold in line 5, we use retraction R at Mk to move along the manifold. We have the following theorem of convergence for Riemannian-CG. Instead of directly proving the convergence for the objective function f, we instead show it for g, which is a regularized version of f. Yet in practice, we can approximate g with f by taking very small values of nu. The space and per iteration time complexity of Riemannian-CG is given below. We use ADMM to solve the linear regression problem shown in equation 7, where ZZ transpose is equal to M star, which is the solution given by Riemannian-CG. The test algorithm is the same as SLEEC. In algorithm 3 and 4, we present RXML train and test algorithms. During the training process, we use k-means clustering, which can be unstable while clustering large datasets. To tackle this issue, we use ensemble learning over the training data, where k-learners are simultaneously trained over the entire data. During the testing phase, we combine the local embeddings obtained by each learner to get a better prediction score. Experiments were done on several publicly available multi-label datasets. We have compared our method RXML with several state-of-the-art methods from each category. We have not compared against the recent deep learning methods as they are computationally very expensive and require several GPUs, yet the train time is usually greater than 10 hours for larger datasets. Here we show the effect of hyperparameters on the precision scores for RXML and SLEEC. In figure 1, we observe that the P81 score is saturated after 30 iterations. Thus, setting maximum iterations to 30 gives a decent score with less train time. Figure 2 shows that increasing the embedding dimension gives a better score, but only up to a certain threshold. Further increase in score is not seen, probably due to the limitation of the model. Choosing a lower approximation rank is crucial, otherwise the model size and the per iteration complexity of Riemannian-CG increases. In our implementation, we have parallelized the training over learners so that the total train time is close to the train time of single learner. However, the model size is directly proportional to the number of learners. As indicated in figure 3, generally 5 to 10 learners are sufficient to get good precision scores. Increasing the number of clusters is also crucial in reducing the per iteration time complexity of Riemannian-CG. As seen in figure 4, increasing the number of clusters does not necessarily alter the score. Hence, we choose a large number of clusters. In figures 2, 3 and 4, we see a similar performance of RXML and SLEEC in terms of P81 scores. In this table, we show the train time, test time and model size of RXML compared with some of the baselines. We see that RXML is 1.5 to 2 times faster than SLEEC and other embedding based methods. This shows the effectiveness of Riemannian optimization techniques. Overall, our method is first or second fastest in terms of train time across all the methods considered. In this table, we show the precision scores of various methods. We see that the precision scores of RXML is comparable to that of several state-of-the-art methods. This concludes the presentation and thank you.